So this is my lecture on periodic table and electronic configurations. We're going to start by looking at this periodic table, and I'm just going to change it in one little way. You guys might have looked at this and thought, this is kind of a funny shape for a way to organize the elements, right? We know that the 1 means I have 1 proton in an atom of hydrogen. 2 means two protons in an atom of helium. Why don't I just put them in a list? Or why don't I organize them in a convenient little box? Like, why do I have this funny stair-steppy thing? I've got this other set of elements that looks like it was kicked out of the periodic table for misbehavior or something. Like, what's up with the shape? Maybe you didn't think that, but you should have, because any good scientist is going to be like, why? This doesn't make sense. Okay, so hang on a second. I'm going to put this over here. You'll find that some periodic tables actually put hydrogen over here. Hydrogen 1. And some periodic tables refuse to put it either on the left-hand side or the right-hand side, and they just put it up in the middle because it's kind of a crazy thing. But for the purposes of this lecture, we're going to stick it over on the right-hand side above fluorine. Because here's what happened. You started discovering all the elements in 1700s, 1800s. And people start asking, okay, well, what are they made out of? And how can we organize all this flood of information that we have so that it helps us make sense of what's going on here? And some people made some propositions about why this way or why that way, but the person who gets credit for the periodic table as we have it currently set up is Dmitry Mendeleev. And he gets credit because, well, I'll tell you in a second. But essentially what he discovered, and by the way, none of these have been discovered yet, so we're going to ignore this column. He discovered that there was a repeating pattern of reactivity, starting with our lowest mass atoms and moving up to highest mass atoms. So hydrogen at room temperature is a gas. And then our next element here, lithium, because they hadn't discovered helium yet. This is a soft reactive metal. Soft reactive metal. And our next one, beryllium, same thing, a little bit harder, still pretty reactive metal. And then boron, it's a nonmetal, carbon, nitrogen, oxygen, these are all nonmetals. And in fact, we also discovered that nitrogen would make compound XH3, that if nitrogen reacted with hydrogen, would always have this formula. If oxygen reacts with hydrogen, it always makes the formula XH2. This is where X is the oxygen or X is the nitrogen in this case. And then you get to fluorine, which is a gas. Behaves a lot like hydrogen. And then you get to sodium, which is, hey, that's a soft reactive metal. And magnesium, not so soft, but still pretty soft reactive metal. And then here we go, silicon, phosphorus, sulfur, nonmetals. Phosphorus, like nitrogen, makes a compound with hydrogen according to this formula, XH3. Sulfur, like oxygen, makes a compound with hydrogen according to this formula, XH2. And then chlorine is a gas at room temperature, just like fluorine and hydrogen. And then continuing on, potassium, next mass up, soft reactive metal, calcium, same thing. We continue across, we get nonmetals. Arsenic has a formula of 1 arsenic to 3 hydrogen atoms. Selenium would have a formula of 1 selenium to 2 hydrogen atoms. And bromine is a gas. So what we see was this pattern of repeating properties and repeating reactivity. So he grouped these together according to columns, so that each column then would have kind of similar properties. Sorry, I have a really hard time drawing straight vertical lines. So everything then in this column has this repeating property of being very soft, very reactive metal. Everything in this column usually makes formula with hydrogen, with one of these element atoms and 2 hydrogen atoms. And he called this the periodic table. Periodic means repeating. anything that happens in a repeating amount of time occurs periodically. So a periodical is a magazine that comes out every week or every 2 weeks. Okay, so the periodic table is a table which is specifically set up to show us how these elements periodically reset and restart the set of similar reactivities. I hope that makes a little bit of sense. And that's why we're putting hydrogen over here with fluorine, chlorine, bromine, because it has those same properties. So that's why we call it the periodic table. The reason that Mendeleev gets credit, because some other people had tried to force the elements into a table, but it just didn't quite work. And he gets credit because instead of trying to force all the information that he had into a table that made sense, he looked at what made sense and then he looked for holes. And he was able to say, for instance, hey, I'm working on this row here, and it seems like arsenic should go here, but because it's the next highest weight after gallium. But really, according to the formula, it looks like it fits here. And so as a result, maybe he said, we haven't discovered this element. And then he predicted it. He said, based on what I found, I hereby predict that there will be an element that will be discovered, and it will have this number of protons, and will have this mass, and it will have these properties. It was pretty ballsy at the time. I mean, really, people have discovered a bunch of elements, and to just tell people, hey, by the way, there's one you haven't discovered yet, and it looks like this, and it acts like this, and it's got this mass. I thought that was pretty cool. So that's why he gets credit, is because instead of assuming that he knew everything there was to know and tried to make sense of it, in the process of trying to make sense of what he saw, he also was open to the fact that he might not have all the pieces yet. And he was able then, by putting in the pieces he did have, to discover what pieces were missing. So a good experiment might help you discover things that you didn't know you didn't know. So that's why Mendeleev gets credit for that. It's pretty awesome. And that's why it's set up like this. So let's look then at the periodic table as it's currently set up, and I'm going to actually copy and paste this in here again. Oh my. I want it to be small like the other one. Here we go. So what we have then are columns, vertical columns. These are called groups. Groups. And we're going to call this group 1, group 2. I'm going to call this one group 3, 4, group 5, 6, 7, and 8. For the moment, I'm going to skip these inner ones. So these are all, anything in the same column is in the same group because they would have similar reactivity. And then the rows are called periods. It's one set of periods that will then repeat itself. Period. Okay. And we have some special group names. I do want you to know some other things that how this ends up being set up. I do want you to be aware of. Since this is the periodic table you get for the exam, obviously none of this information is given. You're going to have to memorize it. But group 1, these are known as the alkali metals. Alkali metals. Group 2 is the alkaline earth metals. Alkaline earth metals. This whole section in the middle that we're kind of skipping over, we're going to call these transition metals, because they transition us from the second column then to the third column. We don't have a particular name that you need to worry about for column 3 or column 4 or column 5. Column 6 is known as the chalcogens, although I'm not going to test you on that, but these are chalcogens. You do need to know that column 7 is known as the halogens. And then column 8, these elements were later discovered. As I told you, they weren't even around. The whole column was missing when Mendeleev did this. But these are noble gases. They don't react. That's why they're noble. So you do need to know that. This section at the bottom that's separated, these are inner transition metals. You do need to know that. This section actually is inserted right here after lanthanum and actinium, essentially splitting the entire periodic table far out so that it can fit that little section of inner transition metals. If you did that, then obviously your periodic table would look something like this. Okay, it would be really, really long, right? Where here's your inner transition metals, and then here would be your transition metals, and then here would be groups 1 through 8. The reason that we put the inner transition metals down here is so that the whole thing fits on an 8.5 by 11 sheet of paper. That's why we do it. No other fancy reason. That's why. Because this is just kind of too long and clunky, that's all. It's not a funny reason for the shape of the periodic table as we see it today. I think it's funny. You guys aren't laughing, but I think it's funny. Anyways, so there we go. Transition metals, inner transition metals, and then we've got kind of an interesting dividing line between our metals and our non-metals, and it goes right here. It's a stair-step dividing line. Okay, and we'll find that atoms to the left are metals, and atoms to the right are nonmetals. So there are by far many more metal elements than nonmetal elements. Okay, this is a great question. Is hydrogen an alkali metal, or does it have properties of an alkali metal? In other words, why am I putting it here? Because this one, hydrogen, is not a metal. It's definitely not. Nope, not an alkali metal. This is it does sit at the top of the group of alkali metals, but it is not one. Hydrogen's a gas, and that's why it is often shown in this position here. But it also often has some of the reactive properties of an alkali metal, which we'll actually talk about in chapter 3. So right after this exam. So next Monday we'll be talking about why do we see hydrogen up here. But it is a non-metal. Thank you for pointing that out, reminding me. So everything else then to the left here is metals, and everything else here is non-metals. And then many of these, silicon, germanium, arsenic, are considered to be metalloids that are on the stair step here. So some of these are metalloids. So what do we mean by metal and non-metal? What are the properties of metals versus the properties of non-metals? Why would we even care? Tell me about metals. I don't know, what do you guys think of when you look at a metal? You're like, I know that's a metal because why? They conduct electricity, good. I'm just using a different color so we know we're talking about the properties of metals. And what else? They can be molded, good. They are ductile and malleable. Both of those are terms that talk about how well you can mold them. Malleable means you can hammer it out to a thin sheet. Ductile means that you can pull it in to a thin wire. So both of those have to do with being moldable. Perfect. Yes, lustrous. What's lustrous mean? Shiny. Yeah, they're lustrous or shiny. They reflect light. perfect. So non-metals, okay, you're okay. Kay wants to move on to the good stuff. So so we're going to say non-metals, by contrast, instead of being ductile and malleable, they are brittle. And they do not conduct electricity. Oh, Shauna, that's a really good question. Yeah. You're still talking about metals. Many metals have relatively high density. So they're going to sink in water. Okay. You're going to get, if you put mercury in water, it's going to sink to the bottom. If you put silver in water, it's going to sink to the bottom. They tend to be relatively heavy for their mass, so they tend to be dense. You guys have to forgive me. I think on your screen, my cursor actually is like a little box, so it's easy to see all the time, but on my screen, it's a tiny dot, and I can never find it. So then I have to like move to somewhere I can and then follow it across the screen. Okay, so they can be dense. They also conduct, in addition to electricity, they conduct heat really well, which is why most of our pans in the kitchen are made out of metal. These numbers here, it's just a way of naming or referring to the column. Is that what you're talking about, Megan? Yep. Nothing fancy except that I'm going to call this 3, 4, 5, 6, 7, and 8 because there's no point in calling this anything but the transition metals for the purposes of this class. All right, so non-metals then, we were talking about, they're brittle, they do not conduct electricity or heat. They're not really shiny. They're basically not metals. That's what we can say. Their properties are the opposite of that of metals. And then metalloids, can you guess what kind of properties they have? Half and half. I mean, it depends on the metalloid, but that's good. They end up having some properties of both. And we would say, for instance, silicon is a non-metal that sometimes acts a little bit like a metal, and say antimony is a metal that in some ways might act a little bit like a non-metal. But say, for instance, for silicon, it's brittle, but it's also shiny. So it looks like a metal, but then if you tried to work with it, you would find that immediately that it's brittle and it doesn't conduct electricity. So it's kind of a little bit of both. That's what we're looking at for metalloids. Okay, perfect. So if we go over here to our in-class activity sheet, section 5, parts A and B here, we've only got about 15 minutes left of class, so I don't want to spend too much time on this, but I think that you guys can do this. Just look at the symbol and tell me, are those metals, non-metals, metalloid? If there's a group name, then you can tell it. And then for part B, you're going to say, group together those which would behave in a similar fashion. So in this case, for part A, you're just going to say, where is this on my table? What can it tell me? So AG on my table is right here. So you're going to say for your answer, this is a transition metal. And chlorine is in group 7. So this is a non-metal, and a halogen, because that's the group name, that column name. And then how are you going to know which ones have similar reactivity? What are you looking for there? The group. Perfect. Not the row, but the group. Because remember that it's the column or the group that has the repeating pattern of reactivity. So in the case of chlorine, I'm looking for whatever other element listed in that group of elements that's in the same column. It could be fluorine, it could be bromine, it could be iodine, kind of a thing. For silver, I'm going to look for anything else that's in the same column. Turns out that copper, silver, gold, all in the same column, so similar properties. Does that surprise you, or does that make perfect sense that copper, silver, and gold should be in the same column? Yeah, I hope that makes perfect sense. Those are all the coinage metals that we make money out of, essentially. Have really similar properties. So if we're looking here, we would say chlorine. Once you went through all of these, you would see, oh, okay, iodine's a halogen too. So we're going to have chlorine and iodine in the same group. We said we had silver and copper were in the same column, so those are going to be in the same group. Okay, I'll let you guys do those because we have got to talk about electron configurations. All right. Now, before I start talking about electron configurations, I want you all to put down your pencils and your paper and just watch, because I'm not going to test you on this, but I want you to be exposed to it and know what I'm talking about when I refer to it later. But it's kind of complicated, and I don't want you to be kind of struggling to keep up with notes. I just want you to watch. Okay. The next question that any good scientist would have once we've discovered this repeating pattern to the periodic table is why? Why is it that hydrogen, lithium, sodium, potassium have similar reactivity? Why is it that fluorine, chlorine, bromine, iodine have similar reactivity? And why is it that it goes in this regular pattern of it looks like about, say, 7 or 8 columns, and then we start over again? That's weird. What the heck is going on? And you shouldn't be surprised to know that this has to do with the subatomic particles, because that's the difference between lithium and chlorine and phosphorus and potassium is the protons, neutrons, and electrons. And specifically, we're looking at the differences in the number of electrons and how they're configured, because it's the electrons on the surface that encounter each other when atoms try to react with one another that determine whether or not that reaction takes place. So we're going to call this next section electronic configurations, because we're looking at how the electrons are configured on the exterior surface of the atom. So here we go, electron configurations. And there's a lot of awesome math and physical chemistry that went into discovering these, and it's going to feel like I'm just spouting nonsense, but I promise this is true, and I'm not going to test you on it, but just follow along, okay? Electrons are confined to discrete areas called orbitals. You could look at that as areas electrons can, quote unquote, orbit, although that's not really the best way to describe it because they don't follow clear patterns. But here's your nucleus. You could say the electrons are confined to these very specific discrete areas. They can't just be anywhere. It's not just a big soft puffy cloud of electrons, but they can only be in very specific places. And those specific orbits or those specific places have discrete energy levels. So in other words, my electrons can only have a very discrete energy level. I could be at energy level 1 or it could be at energy level 2, but I can't be anywhere in between. I can't be like energy level 1.5. I can't be there. All right, I've got to be at 1 or 2. And so the energy levels possible are going to be called shells. Let's see. So we have energy levels, which I'm going to call shells. And we have, let's say, energy level 1, 2, 3, 4, and so on. In each shell, I have some possible subshells, and each additional shell has additional possible subshells. And we're going to subshells call them, we've got S subshell, the P subshell, the D subshell, the F subshell. There's theoretically then a G and an H subshell, but we haven't actually discovered any elements with that many electrons to fill those subshells. So we're just going to stop there. And each subshell has a different shape. So the first energy level only has access to the S subshell, and the S subshell looks like a sphere. The second energy level, or the second shell, has access to both an S subshell and a P subshell. Now this S is the same shape as that S, but it's different because this is a level 1 S and this is a level 2 S. They're both spheres, but the level 2 S is bigger, a bigger sphere than that, so that's a bigger sphere. Okay. And then for each subshell, you've got available orbitals, and the level 1 subshell only or the level S subshell only has 1 orbital. Level P subshell has 3 orbitals. The level D subshell has 5 orbitals. Can anybody guess how many orbitals the level F subshell has? 7. Beautiful. Okay, so there's a little bit of a pattern to it. And orbitals, again, these are the places that the electrons can reside in. And each orbital can have 2 electrons. All right. So the P subshell then has 3 orbitals, and they're shaped kind of like dumbbells. And I'm going to draw this as like in the X or the Y axis and the X axis, and then like the Z axis. Okay. And so then each of these can have 2 electrons. So my S orbital can have 2 electrons. It can have 2 electrons. This one can have 2 electrons. That one can have 2 electrons. This one can have 2 electrons. All right. The level 3 subshell has access to a level 3S, which is a much bigger sphere, and a level 3P, which are then bigger dumbbells, bigger figure eights. And then we also have access to the D subshells, and these ones look goofy. They're kind of like 4-leaf clovers. So there's, let's see, this is like XY axis, XZ axis, C, YZ axis. I can't even, it's hard to draw without my axes. And then you have one really funky one. You're going to think I'm making this up, but I promise I'm not. It's like a donut surrounding what looks like a big p orbital. I promise I'm not making these up. But then again, okay, so there's 5 of these, and each of these can contain 2 electrons, 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 2 electrons. So the level 4 has a level 4S, level 4P, level 4D, and then also has access to the level 4F. And I'm not even going to draw those because they're just crazy out there. Okay. And again, each orbital can hold 2 electrons. And this is how they fill. They fill in order of energy level and subshell level. Just generally speaking, that one energy level shell is lower than the level 2 energy, which is lower than the level 3 energy. That doesn't always follow because the S is lower in energy than the P, and the P is lower in energy than the D. So we get kind of a funny crossover where we end up with the level 4 is higher in energy than the 3, yes. But the highest energy level on the 3, which is the D, ends up being higher in energy than the lowest energy of the 4, which is S. So there's kind of a dirty device here that tells you how to fill these in what order. Again, I'm not testing you on these, so you don't have to be able to do all of this. But essentially, it's going to fill the 1S first, and then the 2S, and then the 2P, and then the 3S, and then the 3P, and then the 4S, and then the 3D. So it kind of goes in this funky order. But knowing that, okay, let's come back up here. And by the way, remember, you've got 2. So you can fill the 1S with up to 2 electrons, and then you can fill the 2S with up to 2 electrons, and then you can fill the 2P with up to how many electrons could you fill in a p orbital? 6. Perfect. And then you can fill the 3S with up to 2, and you can fill the 3P with up to 6. And then you would actually skip down to the 4S, which is up to 2, and then the 3D, which can hold how many? How many would the D one have? 10. Yes. So I've got 5 orbitals they can each hold 2, so 3d10, and then so on and so forth. That's the order that they fill. So I want you guys to watch something that happens here. I'm just going to erase. I'm going to get a big eraser. Watch what happens here. When I look at the electrons filling for everything in group 1, the test has about 25 to 30 questions, Shauna. So hydrogen only has 1 electron, so that 1 electron goes in the level 1 shell, S subshell, there's only 1. Lithium has then 3 electrons, so when it's neutral, so the level 1 shell is full, then the level 2 shell, lowest level subshell, gets 1 electron. Sodium has 11, so we're going to keep going till we get up to 11. Got 2 from that one, 2 from that one, 6, that gives me 10. What do you guys notice about hydrogen, lithium, and sodium that's the same? That might help explain why they react in the same way. This is the part that you're going to have to start paying attention to. You're going to need to know. What do you mean by they're all missing the same number of electrons? What do they miss? I mean, they have as many electrons as they need to be neutral. I know what you're getting at, but I think you're getting ahead of us a little bit. Okay, Shauna says valence. So you're using words we haven't introduced yet, but that's okay. So valence means outermost. Yeah, so Katie and Shauna both says your outermost shell, the one that's on the surface, essentially, right? Because we said that level 2 is bigger than the level 1, and the level 3 is bigger than the level 2. So whatever's on the surface of the atom, that's what's going to react. So let's see what's on the surface of the hydrogen atom. 1 electron in an S-type shell. What's on the surface of the lithium atom? 1 electron in an S-type shell. What's on the surface of the sodium atom? 1 electron in an S-type shell. Hey, are you guys seeing the pattern? Could you guys guess then what potassium would look like? You'd have a bunch of stuff, and what would be at the very end? What would potassium end up with? Perfect. 1 electron and the next S-type shell. And as we fill in electrons, we find that everything in the first row is filling the level 1 shell. Everything in the second row is filling the level 2 shell. Everything in the third row is filling the level 3 shell, and so forth. And we find everything in the first 2 columns are filling your S-type orbitals. Everything in these next columns are filling our P-type orbitals. Everything in this middle section are filling our D-type orbitals, and everything down here is filling an F-type orbital. Okay, so what do you need to take away from this? Because it's about time to go, and don't want to keep you from your next class. Is the number of electrons on the surface of your atom that are reactive, we call those valence electrons, directly corresponds to the group number of your periodic table. Okay, just copied and pasted this from your lecture notes. So everything in group 1 will have 1, in its neutral state, will have 1 electron on its surface. Everything in group 2 will have 2 electrons on its surface. Those are the reactive electrons. Everything in group 3 has 3 on its reactive surface, 4 electrons, and so forth. And everything in the last group has 8, with the exception of helium, which only can have 2. And the interesting thing we find about the noble gases is that these orbitals are completely full, right? This is a full 1s2 orbital. This ends at 2s2, 2p2, full level 2 energy level, full level 3 energy level. That's why these aren't reactive. Okay, that takes us through page 5 for the periodic table of electron configurations. Your job, if you can do it, is to be able to tell me how many valence electrons something has. Here, it's right here. Number of valence electrons in sulfur. You just say, oh, let's see here. There's sulfur, it's 6. Can you guys do that on a test? Please tell me you can do that on a test. Okay. Obviously, your periodic table is not going to tell you, but I think you guys can count to 8. All right, there is just one more section on your in-class activity sheet, part 7, that you do need to know and do. That's just the very last page and a half of our lecture notes. I'm going to have you go over those. It's not too rough. I want you to do that yourself. So, and then I'm going to stop this recording and let you go because we're a little bit over time here.